So this is session number 3 of Newton's laws of motion. So very quickly we will review the concept that we discussed towards the end of the last lecture, which was the concept of how to solve Newton's second law using what is called the free body diagram method. Right, so free body diagram method. In this, what we do is first of all, the body on which we want to apply Newton's second law, the body or object, etc., which is being analyzed. This is represented as a point mass, okay, or particle. So that is like the first step. Okay. And the second step is we draw all external forces acting on it as vectors originating, that is vector arrows from the point mass. Okay. Now next step becomes very critical. Okay. Next step, we resolve the forces according to a system of axes such that, or system of axes, okay, which is convenient with respect to its motion, whatever the motion of the body. So I'll explain in examples what we mean by this third one. And once we have resolved the forces, we apply Newton's second law, which is that net force acting on a rigid body is mass into acceleration. But we apply this in component form. Okay. So that also how we do it exactly, I'll explain. So we can make a quick review of this concept which we've discussed in this last lecture. Yes, Itanshu, I'm aware of that. You are having major test 2. So till the discussion mostly of today's session, we will not be discussing any revision work. We have one more session for that later in the week. Okay, so let's carry ahead with this with another example to make these steps clear. So in my next example, what is happening is we have a block like this. Okay. on a smooth horizontal surface. Block of mass 5 kgs is placed on a smooth floor. Okay. Now, in addition to that, we are applying an external force like this. Now, a constant external force F of magnitude 10 newtons and direction theta equal to, say, 37 degrees with respect to the horizontal starts acting on it. So we have to make the free body diagram, which we refer to as Fbd, of this block, and find its acceleration and normal reaction force on it. Take g to be 10 meters per second square. So just start working on this question. Apply the concept of free body diagram that just we have discussed above this. Okay. So you have to just apply this concept of free body diagram. This only is called FBD. So this concept has to be applied over here. Yeah, okay, students. So sorry about that. Some technical issue, and I was unable to connect online. Anyway, so I'll just share the screen again. Just hang on a second. Yeah, so let's go back to that question we were discussing. I think one or two of you had given me the answer for the acceleration also, but since I was logged out, you will have to send me the messages again. Okay. Ah, Uday. Okay, so 2 meters per second square is the answer you're getting, is it? So let's check out. So first of all, we have to make the free body diagram to understand how many forces are acting on the body. Okay, and no, in fact, we will see that the acceleration will be less than 2 meters per second square. Now the reason for that will be this. I'll explain. So देखो क्या है? The block is lying on the ground. Okay, so I'll show it like a point mass, like a very small one. Okay, but what are the forces acting on it? There are in all three forces acting on it. One is the external force which is acting like this. This is a force of magnitude 10 newtons, right? Yeah, 10 newtons, but it's acting at an angle with respect to the horizontal. It is acting at an angle of, if I draw the horizontal axis here, an angle of 37 degrees with respect to the horizontal. Then there is of course the force of weight, which always acts vertically downwards. So mg, and mg का magnitude यहाँ पे कितना होगा 5 into 10, so that will be 15 newtons. Okay. Because it's lying on a horizontal surface, so the surface will apply an upward normal reaction force. So in all, we can see there are three forces acting on the body. So this is the free body diagram. Three forces: external force or force applied by an external agent, weight, okay, and normal reaction force. These three forces are acting. Now, under the action of these three forces, we can see that the body will slide along the horizontal direction. So its acceleration will be along which direction? Its acceleration will be along the horizontal axis. So it will have some acceleration like this. Okay. And the block slides along the horizontal surface with acceleration E. Okay. Now, because my direction of acceleration is along the horizontal axis, how I should take my axis? I should take the horizontal direction as my x-axis, and I should take the vertical direction as my y-axis. Okay. So, because acceleration is along horizontal, okay, therefore x-axis should be taken along horizontal. Okay. So we have reached how far in our free body diagram method? We have reached up to the second step where we have shown all the forces. But now what we need to do is we need to resolve the force. So to resolve the forces, we need to decide our system of axis. So why we have taken our system of axis as x-axis horizontal and y-axis vertical? Because the acceleration of the body is along the horizontal. Okay. So as you can see, we have done these steps. We have shown the forces acting on the body. Okay. Now we need to do the next step, that is resolve the forces along the axis which is convenient for us. So this particular diagram here, it is called the free body diagram. Okay. So next what we need to do here is we need to resolve F into components along x and y axis. Mg and normal reaction don't have to be resolved because they are both anyway only vertical forces. Okay. So next step in this free body diagram, I need to resolve F. Given a diagram, I need to resolve F. Okay. So when I resolve F, what will happen is that the component of F that is lying along the x axis will become F cos theta, and the component that is lying along the y axis will become F sin theta. So this is how the resolution is done. I hope all of you remember the steps of resolution. So we have a force like this, which is at an angle theta with respect to our system of axis, such that with the x axis it is making an angle theta. Then the x component of that force, the x component becomes how much? It becomes a cos component. And the y component becomes how much? It becomes a sine component. Okay, so that step we are applying over here. ये component कितना है? It is f cos theta, and this component is how much? It is f sine theta. So this is from your vector algebra that you just learned in the previous. Okay. So this force was 10 newtons, and this angle was 37 degrees. So this f cos theta will become 8 newtons, and this f sine theta will become 6 newtons. So this will be 8 newtons. This will be 6 newtons. Okay. So in the diagram, we have replaced this force with its components. Now the other forces we don't need to replace with components because they are already in the correct direction. So normal reaction and weight, we can just leave them the way they are. So normal reaction जैसा भी force है, it is pointing vertically upwards. Whereas mg, we know the magnitude of mg also, and of course the direction is vertically downwards. The magnitude of mg is 15 newtons. Okay. So now in this diagram, we also know that the body has an acceleration along the x-axis of a. So this is a free body diagram with force resolved. This was the original free body diagram. After resolving the force F into its components along x and y axis, we have got this. Yes, that's correct, Rishi. Acceleration will become 1.6 or 8 by 5. Normal reaction force will become mg minus f sine theta actually. Okay. So mg being 50 and f sine theta being 6, it will become 44 actually, the normal reaction force. So let's understand how. So now next step what we need to do, we need to solve Newton's second law, that net force is equal to mass into acceleration. So अभी इसको components में लिख लो. Okay. So this equations x component. So along the x-axis, what is the net force? It is F cos theta. There is no other force. And what is the acceleration? It is a. You can see because the acceleration vector is along the x-axis only. The acceleration vector is a I cap. So we can say that the x component of acceleration is a, the y component of acceleration is 0. Okay. So accordingly, the y component will become such that the net force along the y-axis is how much? It is n plus f sine theta minus mg, but that should be 0. Why? Because the y component of acceleration is 0, whereas this is the case because the x component of acceleration is e. So we get two individual component equations. Equation 1, let's say, along the x-axis, and equation 2 along the y-axis. Now each of these equations will give us one unknown quantity each. First one will give us the acceleration, the second one will give us the normal reaction. So effectively this is how we apply Newton's second law from the free body diagram method. Now follow all the steps of the Fbd method here. First we've drawn the body as a point mass and showed all the forces acting on it as vector arrows. Okay. Next thing what we've done, next thing we've resolved the forces according to our choice of axis. So how do we select our axis? Whatever is the direction of motion, that should be taken as one of our axis. So here the horizontal acceleration is happening. So we should take horizontal direction as our x-axis. That too towards the right. Okay. And once you selected the axis and resolved the forces, then we have to basically apply Newton's second law, which is this one, but in component form. So along the x-axis, net force is mass into acceleration. Along the y-axis, net force is mass into acceleration, but net force only is 0 because there is no acceleration along the y-axis. So just note this down carefully and tell me if all the steps are clear or not. Okay. So from this we will get the acceleration to be f cos theta by m, which when you substitute and calculate, it should come out to be 1.6 meters per second square. And from this you should get the normal reaction as mg minus f sine theta, which when you calculate, it should come out to be 44 newtons. Okay. So these are my two answers. 1.8 कैसे आया था अंशु? 8/5 है ना? Yeah, that's okay now. Okay, so hope this is clear. Let's move on to another example question. Okay, now this time we'll go back to an example of a body on an inclined surface. So this is a smooth inclined plane. Now what we are doing here is we are applying a force on the body An external force is applied in this way, parallel to the inclined plane, to keep the block at rest. So a block of mass 10 kg placed on the smooth inclined plane as shown okay, is kept at rest, that is in equilibrium, by applying a external force okay, along the surface or parallel to the surface as shown. Okay. Take g as 10 meters per second square. So make the free body diagram for the block. Okay. And from that calculate F in newtons. Okay. And also calculate normal reaction in newtons on the block. Okay, so just work this out quickly, people. Okay, so I'll make the free body diagram, but let me give you the answers first. So on making the free body diagram, the value of F should be coming out to 60 newtons. Okay. And the normal reaction acting on it should be coming out to 80 newtons. Now let's understand why. So the weight of the block is a force that will act vertically downwards like this along this vertical direction, and the normal reaction is a force which will act along this sort of direction, perpendicular to the surface. So it will act along a line which is 90 degrees like this. Okay. So you can also see that, like we discussed last time, that normal reaction always acts along a line which makes an angle theta with the vertical, which is the same as the angle that this is making, the inclined plane is making, that is the same as this angle theta. So when we make the proper free body diagram, remember in free body diagram we have to represent the entire body with a point mass like this. Okay. So in that, the three forces that we'll be showing, they will be the ones we discussed about. Normal reaction acting along this direction, mg acting vertically downwards. They should all be drawn treating the point mass like the origin of the vectors. So we draw these vectors like this. Okay. And the external force that we are applying to keep the block at rest, that is acting along the inclined plane. So that will act like this. So in fact, this angle is 90. And also, if we draw our horizontal and vertical like this, you can see this angle is equal to this angle, where theta is equal to 37 degrees. Alright, so hope this is clear. Yeah, so sorry, I got logged out again. So let's come back to this. So these angles are important. So now you can see the forces acting are like this. Now next what we have to do here is we have to balance the forces. Okay. So now this body should be in equilibrium. So we can make use of Lamy's theorem. Okay. Net force should be zero. So you can see here that one way of solving it is by Lamy's theorem, and the other is by resolving. But let's start with Lamy's theorem. So Lamy's theorem, what will happen? N divided by this angle opposite to n, which is 90 plus theta, the sine of 90 plus theta, will become equal to f divided by this angle, which is opposite to f. So that is sine 180 minus theta, and that should be equal to mg divided by sine of the angle opposite to this, which is 90 degrees. Okay. So next step, n divided by cos theta should be equal to f divided by sine theta should be equal to mg. So n should be equal to mg cos theta, which in this case will become how much? It was 10 kg into 10 meters per second square into cos 37, which is 4 by 5, so 80 newtons. And f will become mg sin theta, which is again 100 newtons multiplied by sine 37, which is 3 by 5, so it becomes 16 newtons. So that's one way of solving. Okay. Another way is you can also do by resolution. So if you do by resolution, what you do is you resolve mg into components which are like this, along the inclined plane and perpendicular to the inclined plane. So mg के components will take. So this is mg cos theta. This component will become mg sin theta. Okay. And then you have normal reaction acting like this, and you have the external force F acting like this. So by resolution, now what you do is you take this as your y-axis and this as your x-axis. So along the x-axis, what should happen is F should be balanced by mg sin theta. So this is your equation 1. And see, that will give you this thing here. And along your y-axis, n should be balanced with mg cos theta. So this is your second equation, and this will give you what this equation will give. Okay. So in this case, it's equally easy whether we do it by resolving the forces or by Lamy's theorem. But generally, as I've told you in the last lecture, that when you're dealing with equilibrium of three forces, Lamy's theorem is the easier method of solving. Okay, so hope you are clear about this question fully. Okay, next example. Yeah. So this is a combination of two blocks placed against each other on a smooth surface. And we push this combination with an external force which is horizontal like this. So horizontal force of 20 newtons is applied on a block A which has mass, let us say, 8 kilograms, in contact with block B which has mass of 2 kilograms as shown. So first of all, make individual free body diagrams of A and B. Calculate their acceleration and also calculate the normal reaction force between A and B. Because the two blocks are in contact, so there's some kind of normal contact force between them. So you have to calculate that also. Okay, so the force you're applying is 20 newtons from this side. This block has mass of 8 kilograms. This block has a mass of 2 kilograms. Okay, so let's understand this in more detail. So what happens here is that as we push this block with some force, this will push this block with some normal contact force. And by Newton's second, third law, this will push back with an equal and opposite. So this N is the normal reaction contact force between A and B. Okay. And because of this, they will remain in contact. So what happens is that the blocks A and B will slide together, okay, in contact with common acceleration along the surface. Okay. While of course the vertical forces will get balanced, whatever this one's weight, there will be some normal reaction from the ground which will balance that. Whatever this one's weight, there will be some normal reaction in this. Okay. So now just make the individual FBDs. Okay. Make individual free body diagrams and calculate E and N. Okay, so this should be fairly easy. Just try this out. Yeah, so hope you got the answers for acceleration and normal reaction. नहीं acceleration 2.5 नहीं होगा बेटा because पीछे की तरफ भी normal reaction act कर रहा है ना. So now you see when you make the individual free body diagrams for the block A, for the block A, what all forces are there? We are applying the forward force F, but there is a normal reaction acting backwards. There is mg and this vertical normal reaction, and we don't need to resolve because the forces are already resolved. It has the horizontal acceleration E. Whereas the free body diagram for the block B, now that has only one horizontal force, this contact force N that is acting on it, is only being pushed by this block, no other horizontal force. And this has the same horizontal acceleration A. So now when we apply Newton's second law, that is net force is equal to mass into acceleration. For block E, we'll get the two equations. In the horizontal direction, F minus N is equal to mass of A into acceleration. And in the vertical direction, normal reaction is balancing weight. Okay. So this equation is not required. The first one is the one which is required. For B, in the horizontal direction, there's only one force N, and that is equal to mass into acceleration. So this is the second equation we require. This in the vertical direction, again, this is balancing. Okay. So equation 1 and 2, they're like this. F was how much? Or let's write them first, then we. So just add these two equations, you will get F is equal to. So the acceleration will come out to be. Now you can see the force was 20 newtons and the combined mass was 8 plus 2, 10 kg. So the common acceleration comes out to be 20 by 10 or 2 meters per second square. Now substitute this back in equation 2. You will get the normal reaction. So that is 2 kg multiplied by 2 meters per second square. So the contact force between E and B, or the normal contact force between the two blocks, will be 4 newtons. You can substitute that in equation 1 also, it will give you the same result. So it doesn't matter whether we substitute in equation 1 or 2, because we are solving the equation simultaneously. Okay, so hope this is clear to you and all of you have understood this. Okay, so hope this question is clear. Now we will see another type of force. So earlier we were seeing common type of forces in typical mechanical systems. So far we had seen weight, then we had seen normal contact force, Now the third type of force we'll see today is a type of force called tension. Typically we refer to it with the symbol T. So tension, or sometimes also called tensile force, okay, is the force that acts along the length of a longitudinal kind of body, like a rod or a string or a rope, something like that, of a thread or a rope or chain or even a rod, okay, or for that matter any longitudinally shaped body. Due to external forces acting at its two ends. So basically, if a rope or string is tightened by pulling it, okay, more the tightness, okay, greater will be the tension force in it. Okay, so just note down this sort of explanation of tensile force, then we will understand it with some physical examples. Okay, so as I was saying, let us understand this with an example. So suppose what we've done is, on a smooth surface, we have kept some kind of a rope attached to a hook like this. Okay. So this is a rope, but in a loose kind of state. Okay. Or in mechanics, this is also called a lax kind of state. So in this state, what will happen? The tension acting along the rope's length is zero. Tension is zero. Okay. But next, if we apply some external force on the rope in such a way that this is what tends to get this is what tends to happen, that we are applying a force at one end of the rope and the other end of the rope is attached to the wall. So the rope has a tendency to get stretched out. So it goes from its state of being lax or loose to a state of being tightened, or what in mechanics we call a taut state, T-A-U-T, taut state. So this is some kind of a hook which is used to. Now if we take the rope from that state above to this state below, that it's straightened and it has some tension in it, because what we've done is we have applied some external force on it. So it's changing the state of the rope from being loose or lax to a state like this. So now you can see, under the action of external force F, okay, the rope is now in a what we call tightened state, or very commonly used word for this is taut state, T-A-U-T. Okay. So it develops a force along its length. Okay, and this is called tension T. So what happens is, when we think of the external forces acting on the rope, there will be two external forces actually, because we are pulling it from one end, so the rope has a tendency to move towards the right. But what is happening is that the rope is attached to the hook at the other end, so the hook applies a reactionary force from the other end and makes sure that the reactionary force balances F. So acceleration of the rope remains zero, it remains at rest. So external forces F applied by some external agent and R, that is the reaction force applied by the hook that it is attached to. So what these forces do is act at the two ends, making the rope taut. Okay. And the moment the rope is taut, as a result of this, the rope develops an internal force T along its length. So that internal force acts like this. At this end of the rope, you will see an inward force acting. At this end of the rope, you see an inward force acting. So F and T are actually like an action reaction pair. Now, if you're the external agent who's pulling the rope with your hands with the force F like this, your hands will experience an equal and opposite force opposite to F that you are applying. So that force is nothing but the tensile force, or the tension developed in the rope. So make a note of this, please. So this is the first example for us to understand the concept of tensile force or tension that acts in a longitudinal material like a rope or a chain or a thread, etc., which can be in a tightened state. The moment it is in a tightened or taut state, it develops this force along its length. This develops its internal force along its length, which is called the tension. Okay, so let's understand the most basic example. Yeah, Hitanju, I will answer that question for you. You will understand. So, for example, suppose we have a situation where we are pulling a block horizontally along a floor, but not applying the force directly on the block. Instead, the block is attached with a rope or a chain or something like that, even a heavy chain. Okay. And we are applying the force to that heavy chain. So this is a block of mass. Let's take a big amount of mass. So let's say 100 kgs. Okay. Now what we are doing is we are pulling it using quite a heavy chain or a rope. Okay. So this is a relatively heavy rope, let's say, of its own mass is suppose 20 kilograms and length is, let's say, 5 meters. So that's quite long. And at the end of that, we are applying some external force. So somebody might be pulling the rope with some external force. So F is a horizontal force applied by an external agent to the end of the rope. Okay. So this is a smooth surface. So first of all, make separate free body diagrams for the rope and the block. Okay. And calculate their acceleration. And secondly, calculate the tension at each end of the rope. Okay. So this is what we want to do with it. So just take down the question, I'll explain further. Okay, so what will happen is that the moment we start applying this force, this whole system starts accelerating with some, okay. So both block and the rope move together with common acceleration E. Okay, so what is happening here is we look at the individual objects, what is happening to them. This is the rope, let's say. On the rope, we have applied a force at one end. Okay. So it develops a tension at this end, let's say T1, and some tension at this end, which is, let's say, T2. Okay. So the rope itself is getting pulled by some kind of reaction force, and that reaction force is acting on the block. So these are the horizontal forces. Vertical forces we need not worry about. Okay. So what is happening is here for the rope, the tension at this end is equal to F. The tension at the other end is equal to the reaction force, where R is the reaction force between the block and rope, where they are attached. Whether they are attached through a hook or they are just glued together, whatever, there's some kind of reaction force. Okay, so we have F minus R is equal to mass of the rope into acceleration. That's our first equation. Whereas for the block, we just have that reaction force. So that is capital M into A. That's our second equation. So now solving these two equations, we'll get F is equal to into acceleration. So the acceleration is this much. Okay. So we were applying a force of so I had not given you the magnitude of the force. Okay, so let us say the magnitude of the force is 48 newtons. Let's okay. So this becomes 48 newtons divided by the mass of the rope, which was 20 kilograms, plus the block, which was 100 kg. So 0.4 meters per second square is the acceleration. Okay. And now we can see that in our equation 1, so R is equal to F minus M1. So R is equal to the external force which we are applying, 48, minus mass of the rope. Yeah. Just hang on, people, I'll be back. Yeah, so reactionary force, external force was 48, and mass of this was 20 kg to 0.4. So you can see the reactionary force is 48 minus 8, or 40 newtons. So now from the above equation we can see that tension at this end is equal to 48 newtons. Tension at the other end of the rope is equal to this reactionary force, which is 40 newtons. Okay. So free body diagrams, that was part 1. Then we found out the acceleration of the blocks from this. So this was the answer of part 2. And then we resubstituted this here. So this was part 3. We calculated the tensions. Okay, so people hope this is clear. Okay, now let's look at the next example where instead of dragging a block along a horizontal surface like this one using that rope, what we're doing is we're going to suspend a block from the ceiling, but using a heavy chain or a heavy rope. Okay. This kind of situation. So this is a block of mass 50 kilograms. Okay. And this is a rope, relatively heavy rope of mass 10 kilograms, and g is equal to 10 meters per second square. So this end of the rope is A and this end of the rope is B. Make free body diagrams for the rope and block and calculate PA and TD, that is the tensions at the two ends of the rope. Okay. Now this is an important example. Through this we will understand something more general and more important about ropes and strings. So just work this one out quickly first. Okay, so what you'll understand here is that this is the chain and or the rope, whatever. This is the block. So this is only the tension at the end point B. Okay. And on the hook, whatever force is acting, that is only the tension at the end point E. So the hook is experiencing a downward force. Okay, so that's why we show the forces like this. This is the tension at the end point A. This is the tension at the end point B. So this is the force that the rope at the point B applies on the block. Okay. So now when we talk about the free body diagram of the rope, what is happening is on the rope, there are three forces in all which are acting. Its own weight, okay, the tension at the upper point like this. Okay. And when we think about the free body diagram of the block, so on that there are two forces acting. Its own weight, which is capital Mg, this is small mg, okay, and the force, the tension which the rope is applying on this. Okay, and of course on the hook, the question hasn't asked, but the hook is experiencing a downward force equal to this tension. So this is at rest, this is at rest. So we got our free body diagrams. Okay, that part is done. Now from the second one, you can see that tension in the block. I mean, for the block's free body diagram, you can see that this should be zero. So the tension at this end of the rope should be equal to the weight of the block, which is 500 newtons. Okay. Whereas from the rope's free body diagram, you can see that TA balances the sum of TB and small mg. So the tension at the upper end of the rope is equal to the sum of tension at the lower end plus its own weight. So that is nothing but capital Mg plus small mg. So at the top end of the rope, the tension equals to the combined weight of the rope plus the block. So that is equal to how much now? That is 550 newtons. No, sorry, 600 newtons. This is the tension at the lower end. This is the tension at the upper end. Okay. So what happens is, this is the case of the heavy rope. Okay. But most of the time in mechanics, we'll be dealing with very light ropes or light threads, where the mass of the rope or the thread is negligible compared to the mass of the block. So imagine instead of 10 kgs, if it had been 100 grams or something, that is zero point 0.1 kg, then there would be hardly difference in tension between the two ends. One end the tension would have been 500, the other end the tension would have been 500, 501 newtons. So that is why tension is, so that is why we will follow a simple rule of thumb from here. Okay. So here, in the case of a light, or what we call massless, massless means extremely low in mass. Okay. Massless means of very small mass. It doesn't mean zero mass, because nothing can be exactly zero mass. Thread. Okay. The tension will always be uniform. at both ends. In fact, at all points. Okay. So that you can understand like this only. If you replace this with a thread whose mass is very small, like mass is, let's say, 50 grams. Okay. But you have the same block, it's 50 kg. Okay. Then you will see that the tension which you are getting at the two ends will be such that like this, because it's only 50 grams. Okay. So you'll see that TA is nearly equal to TB. So from that it follows that if M is very very small compared to capital M, then tension will be uniform. So this is an important thing that we will look at in Newton's laws from this point onwards. That whenever we talk about a light thread or a massless thread, which is most often the case, okay, the default type of thread or rope that we use in Newton's laws is not the heavy rope; it is going to be the light thread. So the light thread has this property that the tension will always be uniform at both ends as well as at all other points throughout its length. Okay, so this is going to be very important for us when we come to pulley systems, etc. In the next lecture of Newton's laws. Okay. So we will conclude today's session here. Now, in the next session, we will discuss some of the questions from the assignment, and we will also discuss some revision questions if required, because we have a test coming on Sunday. So it really depends on how well you are prepared for that test. So we'll take it from that point onwards. So please prepare properly, especially the last part of vectors, okay, cross products, applications of products, projections, and all those things. And collect any doubts if you have anything, so that we can discuss that on Friday's lecture. That's it for today's class, people. All the best.